Okay, so let's continue on the theories part of the LASSO. So the first question is why L1 regularization gives the like sparse solutions. So this is a question that is quite interesting because I'm just saying like L1 regularization give you sparse regularization and give you the sparse solution, but why? So and let's just give you a little bit very brief idea why this is true. So let's just remind you the objective the objective of LASSO is the following. So it's basically minimization of my parameter W and the loss function of L, and I'm a function of parameter W and the lambda. So this is basically minimization of W of xw minus y square root 2 norm plus lambda of 1 norm. Okay, so this is the objective. I mean, give you a remind of the 5 and 591. This is Lagrangian of the following constraint optimization. So this is the Lagrangian of the constraint optimization. So what is the following constraint optimization is minimization of this objective subjected to the 1 norm is less equal than B. So basically, and B here is basically the upper bound of the L1 norm of the weight. So basically, this is, what does that mean? It's basically, it's upper bound of L1 norm of weight. And then the connection between this is smaller b is corresponding to large lambda. So that means if my b is small, that implies my domain is smaller. So that means I have more constraint that corresponding to the penalty is bigger. So this is a very good picture that gives you the correspondence between unconstrained optimization versus the constraint optimization. So this unconstrained optimization right here is actually the Lagrangian of this constraint optimization. But sometimes this constraint optimization can give us some good idea of what kind of system that we are working with. And in fact, and we can do very similar things for the ridge as well. So the objective of ridge regressions, it's a minimization of this. So the difference is between the 1 norm into 2 norms. So this is 2 norm. In fact, that's the Lagrangian again. For the constraint optimization again, is minimization. So this is, I forgot the square of the two norm. So this is xy minus, sorry, xw and subjected to the two norm. Square two norm is less equal than b. Okay, so this is basically give you a different perspectives. And similarly, you still have this argument that smaller b corresponding to the large penalty of lambda. So it's more like constraint. But this just give you some like different framework, but this actually can help us to understand why this is giving you an sparse solutions. So what we can do is we can plot the contours of the loss functions with these constraint surfaces. So, and I want to remind you, so this is my loss functions. It is a quadratic, so that means the contour of this loss functions will become an ellipsoid. So basically, it could be something like this. Different color here. So say this is a two-dimensional problem. The contour of this loss of this portion right here, which is like this. We know this will be, the contour will be ellipse. Okay, so, and I want to know the constraint of, say, for an L2 regularizations. So this actually, tells me this is actually a uniball and a ball with a radius of the square root of b. So this could be something like this. So that means this ball actually touch the contour right here. This will be the largest, and the minimum values that you can reach right here. So this will be my optimal values, because you cannot choose this point right here, because this is a solution of this and the W hat, which is the least square solutions. So without any constraint, that would be my local minimum. But with this constraint, say this is the radius of the square root of b, the optimal solution is being reached right here. Okay, and from here you can see this is actually being reached at point of, say, this is my W1, this is my W2. At this point right here, my W1 is not equal to 0, my W2 is not equal to 0. So this is not a sparse solution. So sparse solution, that means it's actually one of the component could be 0. Right? So you can see that's basically the L1, so L2 and the regularization. But if we are talking about L1 regularizations, so you are getting something like this. Oh. So it's the same contour. But the differences is Oh, I think this is a pretty bad plot. So, I mean, if this is my constraint for L1, this is something like this. Wait, I would say this is not precisely what we want to draw here. Okay. Okay, just a second. So this is the contour say this plot will be, and constraint will be something like this. So we know that, I mean, again, that will be my W hat right here. This will be my my least square solutions. The difference is L1 norm, so L1 unit ball in R2, it's actually a square, not a circle. So this is W1, this is W2. Okay, so I mean, the distance right here is just saying, I mean, my W1 is less equal than B, so that corresponding to my absolute value of W1 plus my absolute value of W2 is less equal than B. Okay, so this is actually means, so like this point right here is the B. This is minus B, this is B, this is minus B. So you can see right here, and this solution is most likely touched on the tip, and on the tip of the on the y and the W2 axis. So this solution is being reached at LASSO is B and sorry 0 and B. So this is actually a sparse solutions. Okay. So this is, and the plot is not really clear. Let me just show you this plot in the, I mean computer. Oh. So you can see this is actually the plot right here. So this is the same contour right here, but the difference is my constraint is different. So this is L1 constraint. This is L2 constraint. And you can see L2 constraint, I mean, this is my unit ball. The solution is reached right here. This is non-sparse because at this point, and the W1 and W2 are not zero. On the other hand, if we choose the point right here, so, and if we choose a square, which is, I mean, L1 and regularization, then the optimal value is choose on the tip of the, on the on the vertices of the square. So this will enforce the sparse solutions. And of course, we can choose even smaller and even sparse solutions by imposing this Q, which is the norm, to be even smaller than 1. And you could totally do that, but and for example, and this will like and create even like sparse solutions. But of course, if we do that, then this whole problem will becomes very non-convex. So you can think about this L1 norm is the tightest convex relaxation of L0 norm. So that's why that's why it's considered to be an ideal here. So and this gives you some idea and when it will give you the sparse solution and when it will not. For example, if your original least square and the solution is right here, then if you imposing L1 norm and regularization, the solution will always hit these vertices. So that means it will create this and the situation my W1 is precisely equal to 0. If your previous least square solution is right here, then your and apply L1 regularizations, and the solution will be right on this line that corresponding to W2 will become zeros. Either way, you will be creating a sparse solutions. The only time you are not getting the sparse solutions is your and the least square solution is in this window right here. Then this will be reached into some point right here on this L1 regularization. At this cases, if we using this like regularization, and then we will get dense solutions. So as you can see, L1 and the regularization doesn't necessarily always give you sparse solutions. There will be small region that actually can, it's possible to give you non-sparse solutions or dense solutions. But of course, if we choose like LQ ball, this Q is less than 1, you are getting this region like this. You can see and the region to reach the sparse solution will be significantly bigger. The only point that will give you dense solutions will only be this tiny piece of like a pizza slice. And all the point right here will either give you the sparse solution of this point or the sparse solution of this point. Okay. But the issue is if we're choosing this LP, that P is less than 1, then that will be and still being a non-convex problem, it will be almost impossible to solve. And but if we're choosing L1 norm, it will be some convex problems. But LASSO is not strictly convex, so that means that that solution may not be unique. But at least if it is convex, we have a lot of good and the tools can be working on that and to make it very efficient to be calculated. So in the next part, we're going to show how to find the solution for these LASSO regressions. Okay, so but unlike the previous model that we have, in fact, there's no closed form solution exist. So we actually need to solve LASSO regressions. So for given lambda, numerically. So this is something that is different. And one of the reasons there's no analytical solution is because this loss function right here, it's no longer continuously differentiable. It's because, the component of one norm that here, it is non-smooth absolute component. That basically, I want to remind you, the one norm of my W here is basically summation of each component. And absolute value of of each component. So that's why we have to solve it numerically. I'm going to demonstrate and go into details for one method, and I will briefly mention on the second method as well. Both methods are very popular So the first method that we're going to talk about, it's called pathwise coordinated descent. So this whole idea is we can utilize the fact that my loss function, let me just copy the, so my loss function one more time. So first thing is, if we're trying to calculate the gradient of distance, is hard because of this one norm here. But for each component, because we know W and right here is a vector. For each component, if we take gradient of each component, turns out it's easy. Okay, so I mean, this is fundamentally a different and a phenomena. So if we want to using pathwise coordinate descent, this is particularly good if some problem, it's very hard to find a gradient globally, but it is very easy to find a gradient at each coordinate. So, and also, I mean, since everything is convex, so there's some certain guarantees there exist. I mean the local minimums. So this will be very good in general. So the whole algorithm is stated as follows. So the goal is to minimize the loss function of W and and for given of the lambda right here. So first is we need to initialize W hat equal to 0. Or some initial condition that you can choose smartly. And then we're going to talk about what does that mean for smartly mean, and momentarily. And then later on for the next lecture, when we talk about the homework, I will also tell you what does that actually mean to smartly and make choices for the initialization. So turns out this kind of initialization is extremely important. Second is, while it is not converged, so we are going to pick a coordinate J. So this can be picked at random or round robin. It can be either way. So then, in general, what does that mean is I'm going to fix every other coordinate, just trying to optimize for J coordinate. J minus 1, W, and J plus 1. So what does that mean is everything else right here is fixed. The only thing that is different that I'm going to change is the coordinate. All right, so this is the general framework for the pathwise coordinate like descent. I'm going to show you a simple graph. If we have the contour of like this, so think about this is being x and y, so it's just a 2D. Let's say this is W1, this is W2. What does that actually mean for the pathwise and the descent? For example, so I'm going to start with some point right here. I'm going to strictly assume my W1 is fixed. I only optimize for W2, so I will go this way for one step and then stop right here. And say this is my local minimum once if we fix the W1 and trying to find the minimizer with respect to the variable of W2. Then I'm going to fix the W2 and minimize for W1. So with this two step, basically we do this alternatively. We first fix W1, then optimize for W2. Then we fix W2 and minimize and W1. So this is like round robin fashion. Then we keep doing this. And gradually, there's a guarantee if it is convex, we can always find the local minimum with that situations. So the beauty here, right here is if we can solve these problems analytically, that means we don't even need to perform any gradient descent. It's needed. So you don't even need to have any step size to choose, just solve this problem analytically. For this lasso, it just have this luxury that this can be done. And then it is analytical. So let me show you. So, instead of we solve these problems, and we can just find a gradient first. So I want to remind you, and we want to find out the gradient for this part. So that means we are going to grab this one and take partial derivative with respect to W and W, and let's do it and Wj. So Wj of loss function of W and lambda. So this is obviously partial Wj of minus y squared plus partial Wj of the one norm. So, and basically you can see we have a two component right here. And the second component is pretty easy. The partial Wj, one norm, it's basically summation of absolute value of each component. But every other component as constant, the only thing that matters is absolute value of Wj. So this is equivalent is partial Wj of absolute values. So this is, we already know that it is not differentiable. This is equal to 1 if Wj is bigger than 0. It is -1 if Wj is less than 0. So if Wj is equal to 0, what we usually do is, as a convention, we're going to say the derivative is between -1 to 1. It's actually a vector. So this is just a, convention. We know this function is not differentiable at Wj equal to 0. So this just to make sure things are being like, and it transit through if we bypassing Wj equal to 0. Okay, so this is piecewise differentiable. We can, and we have the subgradient, but we don't have all the gradient for each point. So, and that's the minimum requirement if we want to do any kind of optimizations. Everything beyond that, if we cannot even find the subgradient, then basically there's no way we can use gradient descent or like gradient-based methods. So this is the like least requirement to do any kind of optimization here. Now, the more complicated part is the first part. Is this part. So, and I want to remind you, this is equal to W minus W minus Y transpose and itself, right? So, so let me just take one part here. So, and say we want to take partial derivative with respect to this component first, right? So, the only thing will contribute is the Wj, right? So, and everything other than Wj just, that will be gone. So this will be xj transpose. That will be the corresponding columns of Wj will be applied on. And you can do the same thing for, this W right here. So that means we have a 2 component here. So that means we have a 2 here. All right, so that's something that we have. But that's not good enough because right here we have a 1 W here, and this W will contain the information from the Wj and without the Wj's. Okay, so that means we need to separate things up. So this is 2 times of xj transpose of, we're going to write that as xj Wj plus x minus j W minus j minus y. So I want to like and specify the notation. So this is jth column. So this is without jth columns. And the same idea, Wj is the jth component, and the W minus j is, it's like without this like jth component. So this is actually give you the x times of W. Okay, we can actually split up. This becomes 2 of xj transpose xj Wj minus 2 xj transpose So we have a minus sign here, so we're going to move this minus sign. This becomes y minus x minus j, w minus j. Okay. So you can see right here, this has nothing to do with the wj. I'm going to define this as cj. Right here, this is only related to the xj, which is xj transpose times of xj. So this is I'm going to define as aj. Okay, so this is nothing but I'm going to, and the cj, aj has nothing to do with the wj. So this becomes aj times of wj minus of cj. And the most important thing is everything here, aj, cj, wj, they are all scalar. They are all just 1D scalar. Okay, so this just gives you some idea. And again, this is like w minus j, and the w minus j is the like basically the component of vector that you start with the w1 to wj minus 1, then wj plus 1, then wd. So this is actually a d minus 1 vectors. So you intentionally remove out the wj. Okay, with that, we can combine both gradient together. So that means if we try to write down this partial wj of w and the lambda right here, this tells me this is equal to aj wj minus cj plus lambda. Right, so we have this component being the same. Let me using different colors and just to write at different places. Partial, because this is very important. This is equal to aj wj minus cj plus lambda if wj is bigger than 0. And aj wj minus cj minus lambda if wj is less than 0. Right, because we know this is the component of +1, this is the component of -1. If this is actually equal to 0, this is everything basically in between. So this becomes minus cj minus lambda to minus cj plus lambda. Because my wj is equal to 0, so I mean this component here is actually 0 right here. So we only have the contributions from minus cj minus 1 lambda to the minus cj to the plus lambda. All right, so you can see this cj actually has a good meaning here. So cj is basically if we remove the feature of j and how much this effect to the and when we do the prediction of the y's. So this is basically, you can think about this as being the residue of r minus j. So that means I remove the feature of j to see what is the residue of r minus j. So this, this whole idea of this like residue error can tell us how important of this j's features compared to the other features with this current parameter settings. All right, so now we find out the gradient. Then we're going to assign this equal to 0. Right, so that's not easy, right, to solve. So let's solve this quite explicitly. So if wj is bigger than 0, that means we're going to choose the first one, aj wj minus cj plus lambda equal to 0. So that indicates my wj hat is equal to cj minus lambda over aj. But we know this has to be bigger than 0. That indicates my cj has to be bigger than lambda. Right? If my wj is less than 0, then we're going to using the second one, aj wj minus cj minus lambda equal to 0. That indicates my wj hat is equal to cj plus lambda over aj. And we know this has to be smaller than 0, so that indicates my cj has to be less than minus lambda. So at last we know this wj is equal to 0. That would be the situation, everything in between, right? So, and here is the condition that cj is and bigger than lambda. This is cj is less than minus lambda, and everything in between. So that indicates cj should be between less equal than lambda, bigger equal than minus lambda. Okay, so let me just plot out what does that and really look like, right? So this is actually a very interesting function here. So so that means this is, and you can see this is actually a function of cj and the lambda. So wj of the cj hat, so this is optimal wj here, is equal to cj plus lambda over aj if cj is less than minus lambda, is equal to 0 if cj is in between minus lambda and lambda. And is equal to cj minus lambda over aj if cj is bigger than lambda. And we can plot this out explicitly. If this is your cj, this is the wj hat. Your solution, you have somewhere here. So this is minus lambda. This is your lambda here. And the first one will be a straight line with a slope of 1 over aj. So this is 1 over aj right here. Same here, this will be a 1 over aj slope. and everything in the middle, it will be precisely equal to 0. So this will be the solution really look like. So this will be going up a straight line and flatten. And once they hit a 0, flatten out, it becomes all like precisely equal to 0, then going up with the same slope. On the other hand, if we shrink all the lambda into 0, so this will be a different line that has the same slope. That corresponding to the lambda equal to 0. We know when the lambda equal to 0, this corresponding to the least square solutions. For the least solutions, this is basically says my Wj is just being Cj over Aj. Okay. But my lasso says my solution is actually looks like my blue line right here. So that means my regularized estimate of Wj hat basically shifted the dot line up by lambda and down by lambda as well, except the domain between the minus lambda to lambda. In that cases, we will get Wj hat equal to 0. Okay, so but of course the issue here is this whole thing is quite complicated, right? It looks really complicated and you need to consider all these and all sorts of different situations. There is a shorthanded notations as a compact form. So this is being written as something called sine of Cj divided by Aj multiplied by maximum of Cj over Aj minus lambda over Aj and a 0. Or there is a name for this type of problem is called soft threshold. Of Cj over Aj and the lambda over Aj. So let me just show these two are the same, right? So it's quite quite a simple proof here. So we know right here, Aj is always positive, right? Because Aj is actually the inner product of the norm of like xj. So this is always positive. So when Cj is bigger than 0, so that means and this whole thing that becomes and sine of this becomes 1 times maximum of Cj over Aj minus lambda of Aj and a 0. So that means this will be Cj minus lambda over Aj when lambda is bigger wait, that's not when lambda is smaller than the Cj. Yeah. Yes. When lambda is like smaller than Cj, then this term is bigger than 0. when lambda is bigger than C, when lambda is bigger than Cj, when lambda is bigger than Cj, then this becomes 0. Yes, yes, yes. When Cj is less than 0, then this whole thing becomes minus sign of maximum of minus Cj, Aj, minus lambda over Aj, and a 0. So this becomes, if when lambda is smaller than minus Cj, yes, when lambda is smaller than minus Cj, then this becomes minus sign, and the minus sign cancels out. That becomes Cj plus lambda over Aj is 0 when lambda is bigger than minus Cj. Yeah. And you can combine them together. You can see this becomes nothing but our condition right here. It's just the way that you rewrite things in a different ways. But the benefit to write down everything, this is a much more compact form. It will be helpful if I'm actually to do any kind of the implementations numerically, because numerically you don't want to write a bunch of if loop. So if conditions, that will be way too expensive to do. But this is much, much more efficient, can be done and numerically. All we need to do is to get a sign and get maximum values of these two components. So this is more compact and a more appealing form when we implement that in Python. Okay, so this is something that that we can do, and we can summarize our algorithm. So again, first things initialize w hat equal to 0 or smartly. So then all we need to do is pre-compute the weight of Aj, because like weight of Aj, will not change with the W at all. That is, Aj is just being the norm of X chain. So then we are going to find the optimal WJs right here. So if not converged, pick a coordinate J at random, or round robin. So in later of this implementation, I'm going to show how to do this in round robin. In the homework, you're going to do with the random. Compute the CJ. A CJ actually depends on the WJ. So this will be XJ transpose of Y subtract X minus J of W minus J. Okay. And WJ hat is soft threshold of CJ over AJ and the lambda over AJ. Okay, so this is very straightforward. Then you update your weight at round robin. You continue to do this and weight updating, starting from like W1, W2 to WD, then go back to W1, W2 to WD. You do this again. All right, so this is how we actually did that. So this is the theory part of pathwise and gradient descent. In the next lecture, I'm going to briefly talk about other algorithms of lassos, and then later on, I'm going to actually implement this from scratch for this lasso solvers. All right, so that's all for now.